So I'm very pleased to introduce Ben Briggs, who will tell us about the conormal module and the cotangent complex. Ben.
Thank you so much. It's really nice to be here. There's a lot of people here I haven't seen in a long time, actually, so it's nice to see you. Okay, I guess I'll just get started. So yeah, this is about these two things called the conormal module and the cotangent complex. Maybe the cotangent complex has a reputation for being a bit scary, but I'll try to convince you that these are quite similar and not so scary. So let's just get going. Let's see. So part one though is all about this, the conormal module. So let's do some. The setup is always the same. We always just have some homomorphism of rings, and I want it to be surjective. So S is just R mod I for some ideal here. And I think I want them to be local. That's not too important, but I'll say local because it makes things easier. So this is surjective and local homomorphism of noetherian local rings. And I want to assume that the projective dimension of this ideal I is always finite, which is just some kind of background assumption. If you want, you can assume R is regular, because then all of its ideals will have finite projective dimension, and that case is totally good to think about. Okay, so in this setting, we have the conormal module, like this. That's I mod I squared. It is an S module, even though I is an ideal in R, so I is definitely not an S module, but if you think about it, if you multiply this by I, you get 0, so it's a well-defined S module. The name comes from geometry, so in geometry, it goes like this. If you have a closed immersion, schemes of nice, like locally noetherian schemes, then let's call that F, then it's a closed immersion is going to be defined by some ideal sheaf. And if you do the same construction, the I mod I squared thing, this is called the conormal sheaf. It's a sheaf on X. And it is sort of the name normal means that it's dual to the directions which are normal to X and Y. So it tells you something about the directions that you can deform X inside Y. So it tells you about how to deform X in Y, something like that. So it's, for algebraic geometers at least, it's important because of some deformation theory stuff. But I will, I don't know, try to tell you it's important because of conveyance section stuff as well. Okay, so I like conveyance sections, so let's remember what that is. Y is called complete intersection. If this ideal, this kernel of phi, is generated by some elements of R, is generated by a regular sequence. So what that means is F1 is a non-zero divisor in R, and F2 is a non-zero divisor in R mod F1, and so on up to FC. And geometry, sort of in this context, you would say F is a regular immersion because it means that X is kind of cut out of Y by some regular sequence of functions. And let me just say the conormal module detects the complete intersection property. I'll call this CI. You should tell me if I'm writing too large or too small, more likely, or just too badly. So there is this theorem of, I'll try to go down here, Ferrand, and independently of Vasconcelos, but both in the same year in '67, which says that, so again, we're always assuming that this ideal has finite projective dimension, but I'll write it in there just to make sure that it's definitely there. What they proved is if the conormal module is free, then you have a conveyance section. And it's actually an equivalence, but this backwards direction is easier, was already known, and they proved this forward direction. And in this case, it's automatically just free on the generators. I is generated by these generators, and so I mod I squared is generated by these things, and it's freely generated by these if and only if you have a convenient section. Okay, so let's do a quick example. Let's take R to be a regular ring. I'm just going to give like the smallest example of a non-convenient section would be taking this regular ring and factoring by x squared, xy, and y squared. And then you can do, let's work out, so this is my ideal I in this case. So let's work out what the Kernel module is. Well, whatever it is, it's just sort of the S module generated by x squared, xy, and y squared. And this is not free. So these sums here are not direct sums because if we think about it, if we take this first thing and multiply it by a y, we get the same thing as if we took that second thing, xy, and multiplied it by an x. So it's not free. And in fact, you can compute. So this one nice thing about this ring is that you can write down the resolution of its residue field using this bar construction thing. You can be very explicit at things, and you can compute Tor k I mod I squared over this ring S and find that the projective dimension of this is equal to infinity. So not only is it not free, it has infinite projective dimension. And I guess examples like this motivated the following conjecture of Vasconcelos from 78. Which is, so again, I'll just remember to write this in every time. As long as you have an ideal of finite projective dimension, what he conjectured was that if the projective dimension of the conormal module over S here is finite, then you have a complete intersection. Okay, so what he conjectured was that in this theorem, you could kind of quite drastically weaken this to being just finite projective dimension instead of free. And this again, so this is still equivalent, although now it looks a bit weird, because if you think about it, what this is saying that, so as soon as the kernel module has finite projective dimension, you have a convenient section, and that implies that the kernel module was actually free. So it's, if it has finite projective dimension, then the projective dimension is 0. So it's saying what the projective dimension of this kernel module can only be 0 or infinity. So it's some kind of rigidity thing about certain values are just not allowed for some reason. Okay. So I'll just quickly list some evidence because a lot of people worked on this, so I want to include some of this. In particular, to start with, Vasconcelos had a lot of reason for saying this would be true. So Vasconcelos in 78, when it was conjectured, proved that this is true when the projective dimension of the ideal is less than or equal to 1. And a bunch of other cases. We had various interesting cases of low height and low projective dimensions and stuff like this. But moving on, Gullickson, all the way back in 1969, proved something which implies that the conjecture is true if the conormal module has projective dimension less than or equal to 1. So it's, I guess, it's worth thinking about what this means, because if it's, he proved that if the conormal module has projective dimension less than or equal to 1, then you have a convenient section. But then that gives you that the projective dimension is equal to 0. So what Gullickson really proved is that the projective dimension can never be 1. So that's just somehow not, that's excluded. So these two mathematicians, Aoyama and Matsuoka, proved as well in 1977 that it's true when this ideal I is not complete intersection, but almost complete intersection, which means that the minimal number of generators of I is less than or equal to the grade of I plus 1. So when the grade is equal to the minimal number of generators, that's equivalent to having a convenient section. So grade of an ideal is the maximal length of a regular sequence contained in that ideal. And almost convenient section is where you're at most one off from being that. So, and then Herzog in 1981 had this case that I is in the linkage class of a completed section. And lastly, I'll mention this one because this will come up again in a second. In 1994, Avramov and Herzog, wow, I cannot do that. In 1994, Avramov and Herzog proved this in the case where R is a polynomial ring, which is graded. So R is a positively graded polynomial ring over K, which is a field of characteristic 0. And so I is homogeneous ideal of finite projected dimension. So S is also graded. So they proved it in this case. And lastly, recently, I have a preprint on this. It's just true always. Vasconcelos says conjecture is true. Okay. So mainly what I'm going to be talking about is another way of thinking about this and some other firms and some recent work with Srikanth Iyengar about this stuff and where it's been going. So here's a note. One of the cool things about this, say, this result of Avramov and Herzog, and to a similar extent, this stuff, is that both Avramov and Herzog and this result use methods from rational homotopy theory. But in different ways. So this one was doing some cool stuff with DG algebras and this thing called the Euler derivation. And this one, the main ingredient was this object called the homotopy Lie algebra, which might come back at the end of this talk. But what I want to talk about first, though, is part 2, which is about a related result to this. So part 2 is about these things which I think are really cool, which I didn't know about before, which you could call the higher conormal modules. Or what they're really called, or what they've been called before, which we should stick to, is the cotangent modules. Okay, so what I'm going to do is explain what these things are, why. So the idea is that the conormal module actually comes in this infinite family of modules. So the first one, which I'll call C1 of phi, is the conormal module. And then there's C2 of phi and C3 of phi and so on. So these are, from any homomorphism, you get this sequence of modules. And the first one is always the conormal module. And the rest of them seem to be pretty interesting as well, associated to phi. Okay. So similarly to how I mod I, that should be squared, has like a summutative deformation theory, the idea is that these other ones have something weird, which I don't really understand about higher deformation theory going on. Although I'll explain, C2 at least is going to be really familiar, but that's a spoiler. So they come from the cotangent complex. So for the next few minutes, at least, I have to tell you what this is or how to think about it roughly. So the cotangent complex, this really important thing, that has a lot to do with deformation theory, defined by Andre and Quillen and Illusi. And it goes like this. So this is some complex of three S modules, usually written with an L, some variation on an L. I'll go over bold, blackboard bold L, L sub phi, and it's some complex of three S modules starting in degree 0 and graded like this. So the rough idea of how it's defined is you take, I'm going to try to draw a fancy S. So that's a fancy S, which is supposed to be a resolution of my ring S. So you take a free simplicial R algebra resolution of S. So I wouldn't worry if you don't know what a simplicial R algebra is. You may have heard of them, and they're really similar to DG algebras and in general, just like chain complexes, but with a product on them. And I'll do some examples I'll do some examples where you don't really need the simplicial stuff. So often you don't need to think simplicial, you can just talk about DG algebras and stuff. But so the idea is just doing, it's some kind of resolution of S, and then you take this L thing is going to be the Kähler differentials of this fancy S, and then tensor it with normal S. So in the end, you get a complex of normal S modules instead of some weird fancy S stuff. Okay, so the idea, so the way to think of this is what we did was we replaced S with some resolution of it, and then we did the Kähler differentials of that. So this is kind of derived Kähler differentials. So, and I'll also, if you are not so familiar with Kähler differentials, I'll tell you a bit about those in a second when we do examples as well. Okay, so how to read this? Let me just say, maybe nowadays more algebraic geometers are really into this stuff because it tells you all about deformation theory. So I'll just say this is important in deformation theory, but it does a lot of cool stuff in commutative algebra as well. So with this, if you want, you can just take it as a kind of black box that associated to every homomorphism is this complex like this, which is some kind of derived Kähler differential type thing, and that it does the following. And with this, you can do the following thing. So the ith cotangent module is defined, or say of phi is defined by Ci of phi is you look inside the cotangent complex and you do the co-kernel of this map going from I plus 1 down to I, like that. So if you're used to this construction of taking a free resolution of something and then taking, looking inside that and taking the co-kernel of one of the differentials, that's called taking a syzygy. So this is the ith syzygy of the cotangent complex. So hopefully this next proposition clarifies things a bit and makes people feel better about what's going on. So firstly, this L phi, whatever it is, some complex of S modules, it is defined up to chain homotopy equivalence. So this is the usual story of when you're in this kind of situation where you chose some resolution, you could have chosen a different resolution and you would have gotten a slightly different answer, but the answer you get would have been this chain homotopy equivalent to your original thing. So just like doing normal derived functors. So that's okay. And this implies that when you do this thing of looking at your complex and taking the cokernel of the ith differential inside it, that will give you a well-defined answer. Sort of. This is well-defined. Up to a projective S-module direct summand. So when you do this construction, if you and your friend use different resolutions, you might get slightly different answers, but the answers you get will be the same, but maybe one of you will have an extra free module stuck on, or maybe both of you will have free modules of various ranks stuck on. But they're well-defined except for that. And what I'm going to be talking about is their projective dimensions. So sticking on extra free modules doesn't change the projective dimension, so we're safe there. Okay, and here's where it gets fun. C0. So if you've done some things with derived functors, the first thing this works like a normal derived functor in the sense that if you do your derived functor and then you look at the zero part, you get back your original functor. So C0 phi is just the normal Kähler differentials of S over R, just like that. C1 of phi, I already told you about this one. This is I mod I squared. C2 of phi, this, I guess I put a spoiler in the abstract. This is what I write maybe like this, H1 of Ri, goes like this. It is H1 of the homology in the first place of the Koszul complex on F1 up to Fc. So this is what I would call the first Koszul homology. So that's nice. And then I'm actually not sure what a nice interpretation of C3 is, but I bet there is one. I would like to think about that. But they go on forever. There's this whole sequence of things. What I've written here is kind of strange because for these ones here, I'm assuming phi is surjective. It's like I was before. So that's S is R mod I. And for this one here, you may know that if you have a surjective map, then the Kähler differentials are 0. So the two things I've written here kind of don't make that much sense together. So I could write this in a more uniform way where I didn't need to split into surjective and non-surjective cases, but this is still true the way I've written it. And I guess I should also add to all of these that this is all up to projective summands, because it's still possible that you could have stuck on projective modules to all of these. And so this is kind of, one of the main things I want to say is that there's this whole cool sequence of modules, and the Kähler differentials and the conormal module, and then the first Koszul homology, they're the start of some whole sequence of things. So they naturally come together. They naturally fit together in kind of the same framework, and then there's more of them. And so what we're going to do is, so far we've been talking about this one and all these conjectures about this one, and there are similar conjectures and results about these other ones, and forever. I'm going to talk about those. So let's have a look. So these were introduced by Avramov and Herzog in this paper that I've already talked about in 1994. And well, as far as I know, they were introduced there. They may actually have shown up in other places that I don't know about because they seem like it's a relatively normal thing to do. They proved this thing. So in their context, remember, R and S are graded, and R is always some polynomial ring like this over a field of characteristic 0. And in that context, they prove that if C, so if the projective dimension over S of any of these things at all is finite for any I greater than or equal to 1, then you have a complete intersection homomorphism. Okay, so if you think about it, in degree 1, this is the conormal module, and this is the fact that they prove, which I wrote down already above. And so they ask, is this true more generally? And that's the next result of this talk. The answer is yes. So this is with Srikanth Iyengar. So we have a preprint on this, which says, I'll write it out in full. So if our, this is some, let's put it as a local homomorphism. For this one, local is not very important. But this condition is very important, that the projective dimension of the ideal is finite. Then, same as above, if the projective dimension of any of these is finite for some I at least 1, then you get phi as a complete intersection. And actually both of these are reversible. If you have a complete intersection map, then every single one of these will be projective. So, okay. Just as a quick note, this case I equals 1 is the theorem above. And I equals 2 is the corresponding theorem the corresponding result, but using first Koszul homology instead. So that's also true, using first Koszul homology. And let's slide this down because I also want to mention I equals 0. Or I'll just mention it. So I equals 0 case is not included in this, and I'm going to talk about that in a second because that's interesting and still kind of wide open. So about Kähler differentials. But first, it's sort of long overdue that we did some examples. I'm going to do some examples. So let's do some examples of, say R is just a nice polynomial in one variable. And I'm going to do a complete intersection example. So I'm just going to take S to be this modulo some power of X, like this. So this one is a complete intersection. And my ideal in this case is X to the N as usual. And let me tell you sort of what these simplicial resolution-y things look like. So in this case, my fancy S is just going to be, so remember I said it was a free simplicial R algebra, which means you start with R and you freely adjoin some variables. So in this case, it's going to be just one variable. The degree is 1, and its boundary is equal to X to the N. So that is, in this case, a resolution of S. So just as an aside, in this case, so in the complete intersection case where I only have this degree 1 variable, the free simplicial R algebra on Y is essentially the same as the Koszul complex on, I guess, on this X to the N. So what I'm getting at here is that here you don't really need simplicial stuff at all because there's like an equivalence between simplicial algebras generated in degree 1 and Koszul complexes. They're essentially exactly the same thing. If you've heard of the Dolkan correspondence, you just push it through Dolkan and you get exactly the same thing back. You go back and forwards and you can translate between them. So here, when you're dealing with degree 1 things, it's totally legitimately 100% okay to just think of this as being a Koszul complex on some degree 1 variable in the usual way with its boundaries equal to x to the n. So, and in this case, the cotangent complex is, we're supposed to get Kähler differentials of this thing and then do this thing of changing it to S coefficients rather than fancy S coefficients. So here, what Kähler differentials do, or at least what Kähler differentials do when you have a free algebra like this, is they just take your variable, and for each variable, you get like a d of that variable called a differential, and that freely generates a thing. So in this case, it's actually just a free module in degree 1. So this is some just symbol which generates a free module, and it has degree 1. And there's, since this is a complex that only has something in degree 1 and everywhere else is 0, so the differential is 0. The differential is equal to 0. So we can actually just explicitly do everything in this case. C1 is, let's write it in full. It's a conormal. There's nothing in degree 2, and in degree 1 it looks like this. So it's just this by itself. This is free. And I've already told you that when you have, that's the kernel module. When you have a convenient section map, which this one is, you're supposed to have a free kernel module. And in this case, indeed you do. So maybe I'll put like small thick. So that's working. And also all of the other ones are equal to 0. Like that. Okay, so let me do a more complicated non-convenient section example now. So here's a nice example of a non-convenient section map where you take R to be already, so very similar, but already I'm going to factor by something in R, and S is actually going to be the same as before. So like this. So this is not, this by here is not a convenient section, but my ideal is still the same thing, except it's in this different ring. And this R is this hypersurface ring. So it turns out in this case, what you need to do is the resolution starts off the same. You have a degree 1 variable, and you need to use it to resolve that relation. So you set the boundary of that degree 1 thing equal to x to the n. And you need to go a step further to have this z, where z is degree 2. And the boundary of this z thing is equal to, if you think about it, y times, so we're looking for the boundaries to be something in degree 1. And if you think about it, the boundary of m minus n, that's something which is going to be a sort of, it's going to give you a cycle in degree 1. So you use your z variable to get rid of that. And once you've gone 2 steps in, that turns out to be enough. And that is a resolution of S. So I'm still doing this thing where my notation is not indicating that there's anything simplicial going on. So the way, because like what this notation really means is the free simplicial algebra generated by this, and the free simplicial algebra then generated by adding another variable z. But if you prefer to think in terms of DG things, then again, in this context, once again, because we've only gone up to degree 2, you can still do this purely DG. In this case, the free simplicial R algebra on x, no, on y and z is essentially the same as, which means it can be translated exactly into the free divided power. algebra on these two variables again in degree 1 and degree 2. So i.e., depending on what language you prefer, this is like a Tate model or Tate resolution, or what's it called? An acyclic closure. Acyclic closure. Nope. Acyclic closure. Okay, sorry. Okay, so once again, in this case, you can do this purely with a DG thing, and you can say, okay, I'm going to do my free divided power algebra resolution, which is this thing invented by Tate. So anyway, in this case, this cotangent complex with a fancy S is, now I have two variables, and that gives me, in my cotangent complex, I have a dy and a ds. I have these two differentials. This is really always how the story goes. What this Kähler differential thing does is it just gives you a free module with a sum end corresponding to each variable that you added. So in this case, I needed a dy and a dz. And that is in degree 1, and that's in degree 2. And I have a differential now that goes between them. And the differential is going to be multiplication by this thing, x to the m minus n. So we can work out C1 now. It's going to be the cokernel of this map, x to the m minus n. And what does that do? Well, it's s modulo x to the m minus n, which is interesting because that might be free or it might not be. It depends whether m minus n is bigger than n or not. So sometimes free, depending on so I said my n definitely has to be smaller than m, but it could be, it depends whether n is bigger than m over 2 or not. So it's kind of interesting. And then there's C2. This case, C2 of phi goes from, there's nothing in degree 3, and down in degree 2, I've just got my SDZ. So there's 0 here, so that's just S. It's a free module. Is free. Okay, so C1 is maybe free, maybe not, and C2 is definitely free in this case, and all of the others are 0. So there, we had this theorem that's supposed to say that if these cotangent modules, if these CI guys, if these are free modules, or even if they have finite projected dimension, then I'm supposed to have a Communion section. So there's something wrong here. And what's gone wrong is that this has, this ideal I has infinite projective dimension. So this is not an ideal of finite projective dimension, so that theorem does not apply. So that's why it's allowed for these things to be free, even though this is not a Communion section map.
Ben, may I ask a question?
Yeah, of course.
So that was, I was going to ask later, if, what happens if you just assume finite complete intersection dimension? Because if you're detecting complete intersection properties, that seems, but here you've got a complete intersection. So do you have any perspective on why complete intersection can't see complete intersection? If that question makes sense.
Why? You mean why it's not going to be enough to assume finite complete intersection dimension?
Yeah, I mean, beyond the fact that the existence of the examples, philosophically, why I'm surprised by this.
Yeah, now that I think about it, maybe I am as well. But maybe it will clarify once. So okay, so this is an example. This example is what's called a quasi-complete intersection. And it is definitely possible, because if you think about when you have finite CI dimension, you allow all these deformation things to show up, and you can easily cook up kind of quasi-complete intersection type behavior like this. As far as I know, it's possible, but I don't want to. Don't want anyone to hold me to this. That like the corresponding result is true. Maybe if these cotangent modules, maybe if you have finite CI dimension and these cotangent modules have finite projective dimension, that implies you have a quasi-complete intersection. That's definitely plausible.
Okay.
So it's plausible. So what I'm saying is that it's possible that this is the only sort of thing that goes wrong.
Cool. Thank you very much.
I don't know. So where are we up to? Oh yeah, I promised I would talk a bit about the I = 0 case. So if I is surjective, I already said this, that then this C0 is not very interesting because it's just always 0 because it's the Kähler differentials of S over R. Kähler differentials of a surjective homomorphism is always going to be 0. But Avramov and Herzog were interested in this case anyway, so you can look at a non-surjective map instead. You can just take their field, they had a field, right? And look at this instead. And in order to make things work nicely when you have Kähler differentials, you want to have essentially a finite type. Which means that S is a finitely generated K algebra plus also maybe localized at some multiplicativity coset. And K is going to be a field. And then you can think about, okay, so what about omega of S over K? That is then C0 of this map. And Avramov and Herzog. I should, by the way, have asked whether I'm going up to 50 or 1 hour.
50.
50. Okay. Avramov and Herzog did prove this corresponding result that in their context, so when K has characteristic 0 and S is also graded, it is true that if the projective dimension of this module here is finite, then S is a complete intersection. In general, there is a conjecture of Vasconcelos from the same year, from 1978, that says that it should be the case. For this, there are counterexamples in positive characteristics, so you need some extra assumption, which I'll say if S is generically separable. That's some technical assumption, which is definitely true in characteristic 0. And so it means S is reduced and its total fraction field is a product of separable extensions over K. So if you have this generic separability assumption, then it should be the case that the projective dimension of omega S over K being finite implies that S is complete intersection. Again. So this is still totally open, even in characteristic 0. So it's the case C = 0, or the case I = 0 for C0. That just is not dealt with my work with Sri, so we don't know. Maybe we have some ideas, but not many. So this one is still totally open, except it's true in the graded case, graded characteristic 0 by this work of Avramov and Herzog, again 1904. And it's true that it's known independently by these two same people, Ferrand and Vasconcelos, are that they do the case when the projective dimension is less than or equal to 1. And also it's known to follow from the Eisenbud-Mesa conjecture. So there's another conjecture in commutative algebra which has something to do with symbolic powers, which doesn't seem to be related to this, although there's a equivalent formulation of it in terms of Kähler differentials. So it's it's not totally unrelated. And this conjecture does imply this Vasconcelos' conjecture. So I guess you could see. So the same preprint, which has the first firm above about Vasconcelos' conjecture on the conormal module, has an explanation of this in there. Okay, so C equals 0, as I equals 0 cases, who knows at this point. But let's finish off by doing yet another conjecture. Hopefully I have time to get rid of this. This one is due to Quillen, all the way back in 1969. And it says the following thing. So again, let's have this with a surjective map of noetherian rings with the projective dimension of this ideal being finite. Then what Quillen said is if the projective dimension of the cotangent complex is finite, then phi is complete intersection. Okay, so let me explain what I mean by this. The projective dimension of, so L itself is just a complex of projective S modules. And when I say its projective dimension is finite, I basically mean that it's bounded. So i.e. L is, or I should say homotopy equivalent to a bounded complex of projectives. And maybe even more precisely, the free summands of rank 1 of these correspond to the generators of this fancy S, this resolution. So what this means, having finite projective dimension, so what this means is when you do this resolution, you only need finitely many variables. So this hypothesis that Quillen put here is basically saying, I can do the simplicial resolution and it stops at some step. I only need to go finitely far and add finitely many variables. And what Quillen was saying was, if that's the case, then actually I had to have a complete intersection, in which case you only need degree 1 variables. For complete intersection, it stops immediately. So this implies that the projective dimension of this is less than or equal to 1. So it's another one of these rigidity results. Quillen was really saying that the projective dimension of this cannot be anything except 1 and infinity, or 0, 1, or infinity. So it's a theorem of Avramov from 1999 that this conjecture is true. And that was a really impressive proof. It was, again, using this thing called the homotopy algebra, which I mentioned a few times. And it was proving this by some really delicate estimates on the growth of the homotopy algebra, and it was like kind of hard work. So I'll just finish off by saying here's a new proof of this theorem, which is in this paper, in this preprint, which just goes like this. So if L is bounded, so we're proving this conjecture of Quillen. So I guess we're assuming we're in this context and that L is bounded. Then if you think about it, then these are 0 for I, for large enough I, then these things are just 0. So they definitely have finite projective dimension. They're 0, so phi can be intersectioned by our theorem. So, you know, this gives us that this hypothesis that the cotangent complex is bounded. It gives you that all of these are 0 for eventually, but we only needed one of them to be to have finite projective dimension. So it's kind of, we only partially needed the theorem. But anyway, yeah. So then you get to this complete section, so you get that. I should definitely stop. Actually, I have a minute left, but I don't want to start a new thing. Maybe I can, yeah.
Go ahead. Thanks very much, Ben.
Yeah, sure. Okay.
And we'll take questions now. Feel free to unmute or put your questions in the chat.
So I think you answered this, but I'm making sure I'm understanding. So the backwards direction is true too. So if you have the one of these things vanishes,
Oh yeah. So all
does
of
that
yeah. Where's the main?
I guess if I has finite projective dimension, if one of the CIs vanishes, then you also have a complete intersection.
Yes, so it goes both ways on this, that if any single one of them has finite projective dimension, or in particular, if any single one of them vanishes, then you have a complete intersection. And also vice versa.
Other questions? Anna? Oh, go ahead. Sorry.
Sorry, I was going to ask, but do you know when they start vanishing? Because you did show us an example in the beginning where the first two did not vanish, right?
Right. So yeah, if you have a complete intersection, then C1 is non-zero, or C1 is the conormal module, which is a free module, and then the other CIs are all zero.
Thanks.
Other questions?
I have another, but I was trying to save it for the tea, but maybe I'll ask it anyways.
I'll ask mine if you want to hold on to yours.
Oh, okay, go ahead.
So I'm thinking in terms of, right, is there a version of your result that characterizes non-surjective complete intersection maps via Cohen factorizations?
Yeah. So that part of, I think I kept sort of vaguely saying that surjective is not so important. And there's, at this point, that's a kind of like standard theory. And all of this, you can push through that machine and get like the general version where it's not surjective. So, and that's the way to, where these, that's also the way to properly say this. Like what C1 really is in general, if you have a non-surjective map, is you take a Cohen factorization and then it's the conormal module of that surjective part.
But you still have to, so you have to define it in terms of a Cohen factorization. There's not like an intrinsic definition just in terms of the original map.
Well, that depends on how intrinsic you think the definition of the cotangent complex is, because
Fair enough.
It involves, when you work out the cotangent complex, it involves taking a resolution, which is similar to what doing a Cohen factorization is anyway.
Okay, fair enough. Thank you. Other questions?
I have just like a vague question. Have you thought of trying to approach Vasconcelos conjecture for the module of differentials using your result on Quillen's conjecture? Like in a disproving way.
In a disproving way.
I don't know. I mean, I was just thinking maybe it's like the zero is the problem and the theorem you have below, it tells you that you need to have one of the higher ones that have finite projective dimension.
I mean, yeah, I thought about how these things can connect with this, and so far I don't have any ideas. If you're suggesting that maybe it's false, then yeah, maybe it is false. And maybe...
I mean, I have no clue, but when I read the last statement you wrote, it's like, oh, maybe that's why. That's the piece that is missing. Like, it's not enough to look at the module of differential. You need to look at all of these things together to have a sense of what's happening.
Yeah, I wonder if that could be helpful for trying to think about potential counterexamples about what sort of behavior you need to look for. I don't know if there's anyone out there who's convinced it's wrong. I know, but maybe it could be wrong.
I mean, I don't know either. It is fascinating, though, that you mentioned something about the Eisenbach-Mazur conjecture being related to symbolic powers. Yes. And actually, the proof of Vasconcelos with the case projective dimension 1, it's also related with symbolic powers. So it might be something that creates a symbolic power issues when the projective dimension is bigger than 1. I have no idea. But this is like very, I don't know, every time I hear you talking about this, it's very fascinating. I really like it.
Thank you. But yeah, there's a lot of mysterious things still. I don't know about, maybe Eloise would know stuff about this, like if people are searching for counterexamples by computer or something like that. So if that tells you, because that would tell you also about where to find counterexamples for this.
Other questions for Ben? All right, thanks again, Ben. Very, very nice. Enjoyed it.